average BST, equation 10, is the same as the average quicksort analysis, which is equation 3, not EQ3, which is the same. Okay. So, I don't think I have anything more here. So basically, if we go back up here to the beginning of this analysis, we'll see that our result is going to be 1.38 N LGN. That is the sum of the depths of a binary search tree generated from a random sequence. How many nodes are in that tree? N. So if we divide the summation of the depths by the number of nodes, we'll divide it by n, leaving us what? 1.38 LGN. That means the depth of an average node of a binary search tree generated from a random sequence of n nodes. The average depth will be 38% higher than the average depth of a balanced or full tree. The average tree will tend to be very close to balanced. It won't be balanced, but it'll be very close to balance. On average, it's going to be 1.38 LGN will be the average depth using n nodes. Just divide that number by n, and you get 1.38 LGN. The analysis we did yesterday, our solution was n LGN. When we divided by n, we found the average depth of a balanced tree was log n. And this one we found out 1.38 log n. So the complexity is exactly the same. The theta is exactly the same. So this is an amazing result. That if you just take a bunch of random numbers and you shove them into a tree, that tree will only have about a 38% difference on average in terms of depth from a tree. So if you look again of it, so let's imagine what this tree would look like, shall we? So imagine we have a tree that has 1,024 nodes, or 1,023, whatever you like. So its height will be approximately what? If it's a full tree. If you have 1,024 nodes, your height will be approximately 10. Okay. So, and your average depth is going to be 10. Really, we can say 9, but let's just say 10. So now we'll take the same sequence which generated the balanced tree, and we'll sort it, we'll totally unsort it. We'll shuffle it, and we'll sequence it again, and generate another tree. That tree, on average, we expect to have an average depth, not of log n for each node on average, but 1.3 log n. So the height, if it was 10, is now going to be 40% more than 10, maybe height of 14. So this is what we expect. We expect the tree to be, on average, about a height of 14. So two amazing results. One with quicksort, its average case following the best case, theta complexity, and the binary search tree, randomly generated, follows the best case of a full or balanced tree, following the best case. So here's two examples of the average case being the same as the best case. Is that the rule? Absolutely not. That's what happens here. So that's why when you studied in undergraduate school, if you took a data structures course, they showed you how to insert into a tree, but they didn't spend that much time telling you how to balance a tree. There are algorithms that will balance a tree. Not like we did, like DBT, but there are algorithms that will actually balance the tree as you're putting the nodes in the tree. It'll actually rebalance the tree. Something known as AVL trees are very famous for being self-balancing trees. They didn't spend any time on that. Why? Because this average behavior of 1.38 n log n is so close to the best, it's not worth it. Because to balance the tree takes cost. It takes time to balance the tree. More comparisons. How do I do this? Add this node here, shift this node over here. Okay, to rebalance it. This one is fine, but this one is not. Rebalance it. The rebalancing is always pretty small, but it always adds 2, 3, 4 times overhead, and it's just inserting it. If you just insert it, you're going to get this. Now, what's the risk of doing that? The risk is, oh, I know it's going to be 1.38 log n average. Well, what happens if your sequence happens to be increasing sequence? Then, as we say, you're screwed. Because if the sequence is inserting, then you get this horrible skew tree, and if you have a million nodes, you're going to have a million linked lists going down there. It's a disaster. So this is assuming that your data is random. If that assumption doesn't hold, if the precondition doesn't hold, then the postcondition of this result doesn't hold because this is analyzed using equally likely, which means random order. Okay, so that's all I got.